Okay, hi everybody. So this is the second one of the sort of optional lectures that I'm posting in lieu of the two classes that I missed. And sorry again, I'm away in the UK. But today I'm going to talk about deriving the three important statistical distributions and helping you sort of understand what's quantum mechanical about them and how do they involve particle statistics and so forth. Okay, so if you're a physicist, which I guess you all are, there are basically three important statistical distributions. So the three important statistical distributions. Okay, and the first one is the Boltzmann distribution, which says that the probability of a given system having an energy E is 1 over Z e to the minus E over K BT. Okay, a better way to put this, I guess, an equivalent way to put it is that the probability of the system being in some state K is e to the minus uh, E of K over KBT. So E of K is the energy of state K. Okay, and this thing is like probability of being in state K. And this Z is what we call the partition function. It's a kind of a normalization. You sum this e to the minus energy over kBt over all states, and that gives you the partition function. All right. Um, but once you grow up a little bit, you learn there are two other statistical distributions that are important. Um, one of them is the Fermi-Dirac distribution, which says that the probability of a given state K being occupied, so I'll unpack this for a second. The probability of a given single particle state being occupied. Let's distinguish this carefully. Let me write this as n of k. Okay, and I'll write that as the expected number of fermions in state k is 1 over e to the ek minus mu over kbt plus 1. Okay, so this is basically the expected number of fermions in state K. Okay, so Boltzmann distribution holds very generically is the energy of the entire system is proportional to e to the minus energy over kBt. It's not exclusive with the Fermi-Dirac distribution. Fermi-Dirac distribution is giving you answering a slightly different question. It's saying, what's the probability that a single particle eigenstate k will be occupied? And it's like this. So this n of k is either goes between 0 and 1. And generally it looks like we call this thing the Fermi function. And if I were to plot it, okay, it's often written as F, and it goes between 0 and 1. And this constant mu is called the chemical potential or the Fermi energy. And in the limit of, say, t goes to 0, so this is t equals 0, this thing is just equal to 1 when e is below mu. Sorry, this is e I'm putting on the x-axis. And if you evaluate this very carefully, you take the limits sort of carefully here, you find that it's exactly equal to 1/2 when e is equal to mu, and then it's 1 everywhere above, 0 everywhere below. Sorry, 0 everywhere above, 1 everywhere below. And then at finite temperature, you sort of round out this curve a little bit like this. Okay, so this is some low temperature, and then high temperature, it's sort of rounded out even more like this. Okay. You guys have probably already seen uh, Fermi-Dirac distribution, but it's ubiquitous in the world of electrons where we want to know we have a band and a band has different energies, and what's the probability that a given energy eigenstate will be occupied, a given momentum state will be occupied, and that's what the Fermi-Dirac distribution tells you. Okay, so far I'm just quoting results. Okay, now there's one more which is called the Bose-Einstein distribution. You'll see the Bose-Einstein distribution written two different ways, and I want to maybe help you understand why it's written two different ways. So sometimes it's written like this, as 1 over uh, e to the ek minus mu over kBt minus 1. And there's this mysterious minus 1 that in the denominator. And we'll talk about where that comes from. But sometimes it's also written as or. It's 1 over e to the ek over kBt minus 1 without the mu. Okay, so why is it sometimes written with mu and why is it sometimes written without mu? That's a question we'll sort of talk about in this lecture, and you'll understand where these things come from. So notice that this Bose-Einstein distribution, uh, it can be greater than 1, can be much greater than 1 even. If you're going to energies far below mu, then this can be big. Um, and that's just sort of a way of, that's natural because fermions are forced to obey Pauli exclusion. They're forced to not double occupy any given energy state or any given quantum state K. But bosons can, have as many particles in the same state as you want. Okay, so let me just remind you that we have already derived the Bose-Einstein distribution in the context of phonons. So we derived Bose-Einstein in the context of phonons, um, but actually with the derivation we did was generic, and we said that n of k was let me get this right. We wrote it as it was the expectation value of a dagger k ak, which was trace of e to the minus h over kBt times a dagger k ak divided by trace of e to the minus h over kBt. Okay, and we did that calculation exactly. It turns out to not be too hard when you have the Hamiltonian in its diagonal form. So we had diagonalized the Hamiltonian so that it only depended on a dagger k ak, and then the exponential of the Hamiltonian was just the exponential of all the diagonal entries, and if everything was straightforward. And we did that calculation, and it gave this one. So we'll talk about how you get the other version, why it's sometimes written the other way. But similarly, we've now talked about creation annihilation operator for fermions. Um, so just similarly, one could derive, let's not phrase that in the conditional, one can derive, in fact, you probably can, one can derive Fermi-Dirac as a similar sum. So I write nk is now I'm going to do C dagger K, CK, because I'm using C for fermions and A for bosons. And I have to make one difference here, which is I have to put e to the minus h minus mu n over kBt, C dagger K, CK, over the same normalization. So do that sum and you'll get the exact same thing. Oops, sorry, that should not be there. That should not be there, excuse me. Okay, just like that. Okay, do that sum and you'll get the Fermi-Dirac distribution, just like I quoted it up here. Okay. Um, So why is there that h minus mu n, right? Why is the energy e to the minus h minus mu n? You can say that, well, the reason we had e to the minus h over kBt was sort of the Boltzmann rule, which says that the energy of a given, sorry, the probability of the totals of the whole system having an energy E is e to the minus energy over kBt, and now E, the energy became replaced with the operator h, the Hamiltonian. But where does this come from, e to the h minus mu n? Okay, so maybe it's worth talking about the meaning of chemical potential. Okay, and N is now something like sum over K of C dagger K, CK is the particle number, total particle number. So let me make a little aside about what is a chemical potential. And okay, you guys have probably learned this all in statistical physics, but I find that even people who have taken statistical physics tend to forget what a chemical potential is. So let me just give you maybe a cartoon, the cartoon picture. So the cartoon picture is imagine that um, your system is connected to a reservoir with many, that's double, many particles, all having the same energy mu. Okay? So I mean, imagine that the reservoir has only one energy level. This is not literally how, reservoirs work, but you can uh, think about it this way, and it tends to steer you right. So if I have a system, here's my, okay, so let's draw energy on the y-axis, E. Here's my system. Um, my system might have like many energy levels, all with different degeneracy. I don't know, right? Many energy levels. And now I'm going to draw the reservoir here. And I'm going to put just one energy level right here and say there's like just a giant number of particles sitting in that reservoir. So you can imagine there's like one quantum state, but by chance that quantum state has just infinite degeneracy. So there's just a giant number of particles all packed there. So what happens when you couple the system and the reservoir, and sorry, the energy of the reservoir, that's what we call the chemical potential mu. So you imagine all the particles sitting in the reservoir and they all have the same energy mu. Now, when you couple the system to the reservoir, what happens? The particles start falling out of the reservoir and sitting in these energy levels. And if the energy levels are multifold degenerate, then they occupy all the available states and so forth. Um, and they don't go into the upper ones because that would increase the energy of the system. You'd be pulling them from the reservoir to a higher energy level. Okay. Um, so uh, the total change in the energy here. So the total energy of system plus reservoir. Let's put the total, let's back this up. Let's put this total change in energy. total change in energy of the system plus reservoir. Okay, so let's imagine now that like n particles leave the reservoir. Okay, so the total change in energy of the system plus reservoir after the n particles have entered the system is E minus mu n. Okay, so minus mu n is because you took those particles out of the reservoir and you sort of moved them off to infinity or something. Um, and by doing so, you've lowered the energy of the reservoir by minus mu n. And then you put them in the system and you built up the energy of the system to some level, E. So the total change in system is E minus mu n. And that's why at zero temperature, literally everything below the chemical potential is filled and everything above is empty, because at zero temperature, it's just going to its low energy state. But at finite temperature, there's some entropy associated with how the particles want to distribute themselves in a linear system. The reservoir has no energy because there's only one quantum state, no entropy associated with how you're going to arrange things in the reservoir, but the system does. So there's no entropy in the reservoir, or at least you're not thinking about it. So only one highly degenerate, oh my goodness, degenerate state. Okay. And that's why you get E minus mu n instead of just E entering your Boltzmann distribution. It becomes E to the minus energy minus mu n because you're imagining the reservoir has changed energy as well by pulling stuff out. Okay, that's the cartoon picture. Um, and with that cartoon picture in mind, you can derive all these distributions. But I want to show you that uh, actually all the distributions are just an expression of maximum entropy. Okay, so in fact, all three distributions come from maximizing entropy. Okay, so just the statement that the entropy of the system is maximized is enough to give you all three distributions. And I want to sort of sketch out to you why that's true. So uh, let's start with the Boltzmann distribution. Okay, so let's do this in three parts. So okay, Boltzmann. So uh, uh, we are looking for a probability distribution E of E that maximizes entropy. Okay, now entropy you've probably learned to think about in very physical terms as like, you have so many balls arranged among so many boxes or so forth. But entropy is something that a statistical distribution can have in a sort of abstract sense. Um, and so let's put it like this. Um, any statistical distribution P of X has an entropy, and that usually gets called the Shannon entropy. So S how do I want to put this? Okay, let's just write it as S is maybe the sum over all values that I can have. Let's say xi, sorry, minus pi log of pi. That's called the Shannon entropy. Okay, so I labels all possible values of X. Okay, so the Shannon entropy is really like a measure of the entropy of any statistical distribution. When the Shannon entropy is large, it means that you have maximum uncertainty or very high uncertainty about the value of a random variable drawn from the distribution. So like you can calculate the entropy of a dice roll, right? So if you have one die, every outcome has a probability 1/6, and so the Shannon entropy will be minus 1/6 log of 1/6, times six, so you have six possible entropys, and there's a particular entropy associated with that. Um, if you calculate the entropy of like the average score of two dice rolls, right? So you roll two dice, and now like rolling two or rolling 12 is less likely than rolling seven because there's only one way to roll two. You roll 1, 1, only one way to roll 12, 6, 6. But there are many ways to roll seven. You can roll 1, 6 or 2, 5 or 3, 4, etc. So the outcome seven is more likely than the outcome one or two. And now the average score of two dice rolls has lower entropy. It's more likely to be near the middle of the distribution than on the edges. So in general, any distribution has an entropy, and it comes down to like how many, you can measure it in bits, like how many bits of information do I expect to gain from a random draw of the distribution. This is like a very fundamental concept of the entropy of a statistical distribution. Okay, so we want to maximize S equals minus sum over I of PI uh, log PI. Okay, so that's just saying now I labels all energy eigenstates. Okay, so what we're saying is we want to find the distribution that produces the largest statistical uncertainty of the value. So I'm saying like I take a snapshot of the system at random and calculate its energy, and I want that to be as unpredictable as possible. And that's completely equivalent to the usual way of thinking about entropy is the number of microstates. I want it to be as unpredictable as possible, which is saying it's going to tend toward the configurations that have the most microstates consistent with them. Okay. But we have constraints. So we want to maximize this thing, but we have subject to uh, two constraints. Okay. One constraint is normalization. Sum over I of pi is equal to 1. That's normalization. So any statistical distribution has to obey normalization. Okay. And sum over I of pi ei is equal to, let's just call it mm, E E. So the average system energy is well defined. Well defined. Okay, let's call it E average. Okay, so I want the system to have a well-defined average energy. I don't want something where like if I calculate the expectation value of the energy, it goes off to infinity or something. I want to say I'm looking for a distribution that describes the system having a given overall energy. Um, and now, given that the average energy is whatever, what is the probability of different microstates? So that's what I'm looking for. So this is a constrained optimization problem. Okay? You can think that we want to maximize, or we want to find the optimal value of each pi. Okay, so I might have a million different values or something like that. We want to find the average value of each of them. But we have to make sure we're satisfying the constraint that the sum over all pi's is 1 and that the expectation value of the energy stays fixed. Okay, so how do you do constrained optimization problems? The smartest way to do that is the method of Lagrange multipliers. And if you guys have not yet learned the method of Lagrange multipliers, all I can do is say that I'm sorry for you because it's like the greatest technique in mathematics is the method of Lagrange multipliers. And I'm sorry that you didn't learn it in your undergraduate calculus class. But just maybe as a lightning summary, uh, the method of Lagrange multipliers. Okay, probably you guys have all learned it, but I made it to my second year of graduate school without ever learning Lagrange multipliers, or at least to my first year of graduate school, and I felt just so betrayed that no one had taught it to me because it's such a useful thing. But when you use Lagrange multipliers, you write down a Lagrange function that's like lambda equals s, the thing you're trying to maximize, minus some constant. Let's call it okay, lambda n. That's the thing associated with normalization. So sum over I pi minus 1 minus lambda e. This is another constant that's associated with energy conservation. Sum over I of pi ei minus e average. Okay. So the method of Lagrange multipliers is that you take the function you're trying to maximize, that's s, and then you subtract from it some constant times this thing, which should be equal to 1, or sorry, equal to 0, that's one of your constraints, and this thing, which should be equal to 0, that's another constraint. And now you say, I'm just going to maximize this thing with respect to, I want to maximize lambda, which is called the Lagrange function, with respect to all pi's and lambda n and lambda e. That's what you do. Okay, so how do you maximize a function? You say d lambda dpj equals 0 for some let's say for some j, for some value of j. So, inside S is a sum over all the terms, but let's just pick out one of them, like it's say P5, probability of, state 5 being occupied. So then what do we have? We've got d lambda dpj is equal to, okay, let's just write this out. D dpj, and what was S? S was like sum over I of minus pi log pi. And then I've got some minus, oops. Um, okay, let's just write it, fine. Minus sum over lambda n, d dpj, sum over I pi minus 1, minus lambda e, d dpj. Okay, so now it's an exercise in taking derivatives. Um, okay, so let's just to be clear here, this thing right there, that's like sum over I pi log pi is like, p1 log p1 plus p2 log p2 plus p3 log p3, etc. And we're trying to take the derivative with respect to a particular one of them, like p5 log p5. And if you take the derivative, what that's going to give you is you're just going to pick out the one term that you care about, which is some value I equals j. And you're going to get here minus log pj plus 1. Okay, I'm saving you some. Okay, let me do one more step here. This is equals minus d dpj of pj log pj. Only one term in the sum matters. And if you do that derivative, you'll get minus log pj plus 1. Okay. Okay, what are you going to do? What are you going to get when you do this? Uh, that's just uh, that's just going to give you 1. You're going to get ddp. Okay, let's again do this carefully. Uh, d dpj of pj minus 1, and that's 1. And this thing right here is going to give you d dpj. Again, you only pick out one term in the sum. pj ej minus e average, which is ej. Okay, so what are we left with? What we're left with now is minus log pj plus 1 is equal to, sorry, minus log pj minus 1 minus lambda n minus lambda ej equals 0. Okay, so let's just rewrite that. And now I get pj is equal to e to the minus lambda e ej uh, uh, minus lambda n plus 1. So let's write that again. So P of j is equal to e to the 1 minus lambda n times e to the minus lambda e ej. Okay, so this is secretly the Boltzmann distribution. So this is 1 over z. That's just a constant, right? It's energy independent. And this is e to the minus energy over constant. Okay, and so lambda e is 1 over kVt. Okay, lambda e is 1 over kVt. But what this tells you right away is the form of the distribution. It tells you immediately that you're going to get something like a Boltzmann distribution, that the probability of a given of a state with energy E is going to depend only on the energy, and it's going to E to the minus the energy over some constant. And that constant is what we call the temperature. Okay, so it comes immediately just from maximizing entropy. So you just write down the statistical entry of the distribution, and you say, I have to conserve the probability of the distribution, and I have to conserve the average energy. I have to have a well-defined expectation value of the energy. And from that, you immediately get the Boltzmann distribution. Okay, good. So there's nothing, there's nothing. That's why the Boltzmann distribution is so universal. It doesn't know anything about the physics inside the system. I didn't write anything about the Hamiltonian or whatever. So it works equally well for quantum and classical. It's just a statement of maximum entropy. Okay, how about Fermi-Dirac? Um, okay, now let's talk about Fermi-Dirac. So, you're often given the impression that a Fermi-Dirac is a quantum mechanical result. That Fermi-Dirac is like a quantum probability distribution. And that's true in a sense, but maybe not in the way that you think about it. Like the Fermi-Dirac distribution does not have h bar in it anywhere, which means that somehow it can't know about quantum mechanics in the sense of a non-trivial commutation relation between p and x. It can't know about the uncertainty principle or anything like that. Um, so uh, let's think about the entropy associated with a statistical distribution. So what we want, um, what we want to maximize the entropy of a system with n particles, subject now to 3 constraints. Okay. First one is that the total number of particles is n, okay, which I mean that if I sum over all states k of n of k, I better get n. Okay. 2, the total energy is, okay, I guess I'll write it as E total, which means something like if I sum over all eigenstates of EK, NK, I better get E total. So whatever distribution I'm going to write, it should conserve my expectation value of the energy. Okay, 3, we have another constraint, which is that each state can hold at most one particle. Okay. All right. So n of k doesn't have to be 0 or 1. So just to make this clear, so n of k uh, can be a continuous number, in the interval 0, 1. But because it corresponds to sort of an average over all possible microstates, but each microstate must have a given state filled or empty. Actually, let's go back. I want to be careful here not to confuse notation. Let me refer to this n of k as like an average n of k, as this is an average. I want to distinguish it from the occupation of a given sort of microstate, where n of k has to be either 0 or 1. What I'm talking here is the thermal average n of k. So let me similarly go back here and write this thing as n of k, n of k, n of k, n of k, like that. And this n of k is often called just f. Okay, but I mean, this thermal average of n of k is what we mean by the Fermi distribution f. Okay, so it's f of some state k. All right. Good. So let me just make that clearer here. And maybe now what I'll talk about here is fk, and I'll call this f of k. Okay, I mean by this f the thermal average occupation of state k, not the microscopic little n of k that has to be either 0 or 1. Okay, so how do we write the entropy? So let's write the entropy S equals sum over all states I of S of I. Okay, so just to be clear, what I mean here is that this S of I is the entropy associated with filling the single particle state I. Okay, so what does that mean? What do I mean the entropy associated with filling a single particle state I? What I mean is that S of I is sort of, I'm going to again write minus sum of P log P. Okay, but now what I mean here is I'm going to sum over the probability of it being filled or empty. So let's write, I don't know, sigma is filled or empty of P sigma log P sigma. What I mean here, what I mean here, that P filled is what I called F, and P empty is what I'm going to call 1 minus F. That's sort of by definition, right? The probability that it's being filled is what I call, sorry, let's call it F of I. Okay, F of I is exactly the probability that it's filled, and so 1 minus F of I is the probability that it's empty. Okay, so this is again the Shannon entropy of a probability distribution P, sum over states of P log P, but now I'm summing over for a given single particle state, there are only two conditions. It can be filled or it can be empty. Okay, so now I get S of I is minus Fi log Fi minus 1 minus Fi log 1 minus Fi. So um, each single particle level contributes an entropy that's F log F minus 1 minus F log 1 minus F. Okay, so just to make this clear, so S of I equals 0 when F equals 0 or when F equals 1. Okay, you can mentally plug in F equals 0. If F equals 0, this prefactor is 0, but also you're going to get here log of 1, which is also 0. On the other hand, if F is 1, if F is 1, the situation is reversed. If F is 1, then log 1 is 0, and also 1 minus 1 is 0. Anyway, all of that is to say that if a state is definitely filled or definitely empty, it cannot contribute any entropy. Only a state that has some finite probability of being filled and of being empty can contribute any entropy. Okay. So we want to maximize the sum over all I of this quantity. Okay, so we're again gonna use Lagrange multipliers and maximize that quantity. Okay, so what are our constraints? Our two constraints. Uh, okay, let's call it our two remaining constraints. Okay. One was the particle number conservation, which said sum over I of Fi is equal to n. And two was sum over I of Fi EI was equal to some average energy. It had to be well defined. Okay, good. So our Lagrange function is lambda equals, now I'm going to do it like this, sum over I of Si, that's the total entropy of the distribution. Okay, now I have some constraint, lambda n, sum over I Fi minus n minus lambda e, sum over I Fi EI minus E average. And I'm going to require d lambda d f j equals 0 for all j. Okay, now it's an exercise in doing derivatives and rearranging. So I will spare you that part because, you know, this is a lecture that you're watching on Zoom and you have limited patience. So do derivatives and rearrange. Okay, it looks a lot like what we had before. The difference is that for the Boltzmann case, you had a p log p, but now you have both a p log p or an f log f, and this one, 1 minus f log 1 minus f. Okay, and ultimately that second term is going to give you a different form, and what it gives you in the end is f is 1 over e to the lambda fj plus lambda n plus 1. Okay. So just let me just write this differently. That's 1 over e to the, I guess I'll write it like lambda e j plus lambda n over lambda e plus 1. Okay. Anyway, the point is that you should see 1 over e to the constant, energy minus constant plus 1. Okay, so this thing here is 1 over kBt. And this thing is minus mu. Okay? But the functional form of the probability distribution comes just from entropy maximization. All right, now this is the part where you can say like, wait a second, like Fermi-Dirac came out of quantum mechanics, like it's a quantum mechanical result. Where did quantum mechanics enter here? And the answer is that quantum mechanics entered only in the fact that we demanded that every state had to be either definitely empty or occupied for each microstate. So Pauli exclusion is secretly buried in this point, number 3. But other than that, there's no quantum mechanics of any kind. It's just maximum entropy, subject to the fact that any given energy state or any given state can only be occupied uh, by at most one fermion. And you'll notice that, whether energy states are degenerate doesn't matter. Whether every energy state can hold 2 electrons or 3 or whatever doesn't matter. The only thing that mattered was that each microstate, as long as we took the sum to mean microstates, the form of the Fermi-Dirac distribution is completely universal. So there are actually classical situations where you get a Fermi-Dirac distribution as well that have no quantum mechanics in them, but have for some reason a constraint that any given, microstate can only be singly occupied. Like if you are arranging, n balls over n bins and the bins have different energy and each bin can hold one ball, you'll also get a Fermi-Dirac distribution. It's just a result of that exclusion. Okay, good. I remember feeling enlightened when I first went through this derivation and feeling like, oh, like Fermi-Dirac distribution isn't as quantum mechanical as I thought it was. Okay, now let's do Bose-Einstein. All right, here we have to be a little bit careful about the way we think about entropy. So let me try to do this as best I can. So the best way to think about entropy here. Um, Imagine m much, much greater than 1 parallel copies of the system. Okay, by which I mean you have a system in this box that has many particles and many energy levels or whatever, and you have another system in an identical box and with no coupling between the two, and it also has many, it's identical in every way. Okay. All right. So for some energy level I, or so let's just say some, let me not call it energy level, for some single particle state I, um, the average filling across all copies of the system is, let's call it Ni equals capital Ni over M. Um, and this is like number of particles in state I summed over all copies of the system. Okay. This is what we want to calculate. Okay. Let's assume M is very large. So Ni is also much greater than 1. Okay. I've made M my hypothetical number of copies, and I'm imagining my system very, very big. So it's so big that the expected number of particles in state I summed over all copies of the system is also very big. Okay, so what is the entropy associated with arranging Ni much greater than one particles across M much greater than one copies of the system? Okay. So I have summed over all copies of it, Ni particles, but I can arrange them somehow among all copies of the system, and what's the entropy associated with that? And this is like a classic combinatorics problem. And this says the number of ways to arrange n particles among, let's not say arrange, let's use distribute. The number of ways to distribute n particles among m boxes. Sorry, my m's are getting bad. It's late at night where I am. Okay, hold on. M boxes is, uh, let's call it omega I is n plus m minus 1. Choose m minus 1. Okay, so that's just n plus m minus 1. Choose m minus 1. Oops. Okay, if you think about this hard enough, uh, you can rationalize this, but maybe in the interest of time, I won't do it. Anyway, that works out to be n plus m minus 1 factorial over n factorial m minus 1 factorial. Okay. Okay. So the the okay, I'm going to use a weird notation here. This little capital SI uh, is equal to log gamma I. So this is basically total entropy across all m copies of the system. Okay. And that's something like log of uh, n plus m minus 1 factorial minus log n factorial minus log of m minus 1 factorial. Okay. I sort of told you that n and m are both very large, so we're going to sort of neglect that minus 1. We're going to neglect this minus 1. And now what do you do when you've got log of something factorial? And this is where maybe a bunch of you are having Vietnam-style flashbacks to undergrad stat mech and the Stirling approximation. So you use Stirling's approximation, which is like the one math identity you use over and over in stat mech, which says that log of x factorial is approximately equal to x log x minus x for x much greater than 1. Okay. Okay, put that in there and let me save you a little bit of math here. And what you'll get here is to get S, capital S of I is equal to, let me see if I can do this right, M And then I'm going to get uh, ni plus 1 log ni plus 1. Let's do it like this, minus ni log ni. Okay. This thing right here, this is the entropy per copy. And I'll do without subject, just SI without the little decorations on it. Uh, this is the real entropy if you want. This is what we care about. Okay, so this business of making many copies of the system was just sort of a imaginary invention on our part to try to understand how do I think about the entropy. But what we care about now is this thing, the entropy per copy. Okay, so this is and what we, this is what we care about and what we want to maximize. Okay. Or or rather, I suppose what you say, what we want to do is we want to maximize the sum over I of all SI. So what are our constraints? Okay. What are our constraints? So we're again going to have well, actually, let's. So the way we've been doing this is we first always thought about particle number conservation or number conservation. So let me just start with that. So do we have particle conservation? And that's not always so clear. Like if I have a bosonic system, do I have conservation in the number of particles? And that depends very much on your uh, on your setup. So when we talked about phonons, there was no concept of particle number conservation. We were just talking about like a lattice of atoms that were vibrating, and there's no reason why the number of phonons should be conserved. The only thing that had to be conserved was the energy. So uh, for the phonon case, there was no notion of particle conservation. Uh, so the answer is often not. So, for example, in the case uh, of phonons, we had no notion of particle conservation. But sometimes we do. Like if you just have a gas of rubidium atoms or whatever, you know have your container and you shake out 1,000 rubidium atoms, and they're not going to suddenly like merge into one rubidium atom and decrease the number. So sometimes you do, you know. So for example, for bosonic atoms, you have a certain number of atoms, and they're bosons because the total spin, counting all the fermions and electrons, is an integer. Um, but the number is still conserved. So sometimes you do and sometimes you don't. So if you do, then uh, the sum over I of ni uh, has to be equal to n is a constraint. But maybe you don't have that constraint. So let's do it with the constraint, and then let's imagine that you do have that constraint, like you have rubidium atoms or something in a trap. But at the end, we'll look at what happens if you don't have that constraint. Okay. Okay. What's our other constraint? We also have fixed uh, average energy. Okay, which is sort of sum over I, Ni, Ei is equal to E total. Okay, average, let's say total energy. Okay. So those are our two constraints. Particle conservation, we may or may not have it. Fixed energy, we do. So now the Lagrange function. is something like lambda is sum over I of Si minus lambda E. Um, well, let's do this in order. Minus lambda N sum over I, Ni, EI minus E total minus lambda E sum over I, Ni, uh, minus N total, excuse me. And just to remind you, sorry, this thing here was sum over I of what did we have for S? It was Ni plus 1 log of Ni plus 1 minus Ni log Ni. Okay. Okay, good. So now we have a thing we can take derivatives. Let me just point out here that if there is no number conservation, set lambda n equals 0. Okay, so we can recover the case where there's no number conservation by just erasing this whole term, and that's equivalent to just setting lambda n equals 0. Okay, so now take the derivative. E lambda dn j equals 0 for arbitrary j, just like we did before. Okay, and then do the math, right? Take your derivatives, plug it into Mathematica, it spits out some garbage, and then you have to rearrange something sensible, whatever. And you'll get nj is equal to 1 over e to the lambda e ej plus lambda n minus 1. Okay, good. So this thing, lambda e, is 1 over kbt. Okay, and this is equal to, sorry, what did I say before? This is equal to, okay, I guess I said, sorry, let me write it the other way I had before. Let me write it the way I had it before. So that's equal to 1 over e to the lambda e ej plus lambda n over lambda e minus 1. Okay, so that is equal to 1 over kbt, lambda e, and this is equal to minus mu if there is number conservation, and is equal to 0 otherwise. Okay. So it's often said that systems effectively, systems without number conservation, like phonons, always have 0 chemical potential. When new particles can be created, just, when there's no, how do I say this? When there's nothing that stops you from just creating or combining two particles or whatever, just by two things vibrating in different ways or something like that, then your chemical potential is forced to be 0. So phonons, for example, always have 0 chemical potential. Photons always have 0 chemical potential. But atoms in a trap might not have 0 chemical potential because someone put a certain number of them in. And in the Lagrange multiplier sense, you can see how that came about. Okay, so that's all I have for now. I'll post these notes. Thank you guys for watching. But I hope this gave you some sense that like all of those three sort of mysterious statistical distribution functions that we have, Boltzmann distribution, Fermi-Dirac distribution, Bose-Einstein distribution, they're all just an expression of maximum entropy, and there's no quantum mechanics of any kind really at work. The only thing that comes down, that enters our consideration is whether or not we have to think about uh, Pauli exclusion in the sense of can a single state be doubly occupied or not? But um, with that in mind, everything else follows completely universally. And in that sense, there's nothing intrinsically or necessarily quantum mechanical about either the Fermi-Dirac or the Bose-Einstein distribution. Okay, thank you.